Hello, welcome back to the Apache Beam College Intermediate Track, implementing a complex ML pipeline. This is session 2. So last time in session 1, we had an introduction to Beam and the run inference transform and the model handler class that provides the main argument to the run inference transform. Today in session 2, we're going to talk about how to choose a model for a task and how to adapt that model to Beam. So just as a brief review, run inference is the transform that we'll be using for all of our examples and in the pipeline that we build later in this session. So the run inference transform takes as its main argument a model handler that says how to load and how to do inference with a given model, usually for a given framework. And that model handler can have pre and post-processing functions attached, and there can also be error handling and other arguments. Now, when you have a problem that you're using an ML model to solve, there are several considerations that you have to make for choosing a model. Of course, the most important consideration is the function. Will the model do what you need? I find that this can often be more of a challenge than you expect. You may have a task that doesn't map well to a given model, or it may be difficult to find the right model for a task. When I'm looking for a model, I usually turn to Hugging Face as my first stop. It seems to be the biggest model repository these days, and it also has models organized by their function. Of course, an advantage is that we have Hugging Face model handlers, so I know that when I find a model on Hugging Face, it's likely going to be pretty easy to incorporate into my pipeline. The next consideration is the size of the model. Here, we often see that a larger model is more capable. On the other side, a larger model may consume more of your GPU if you're running on a GPU. And you need a model that fits into the chip that you have available to you. So when you're starting looking at models, you'll often see that especially the models that are more polished will be available in a variety of sizes. So it's often advisable to begin with the smallest implementation of the model, do experiments and check the quality of output, and then scale up to the size that comfortably fits in your GPU. The next consideration with models is the framework that the model is available in. For example, TensorFlow or PyTorch. Most models are available in more than one framework. You can get the weights and load the model or a pre-trained model into TensorFlow or PyTorch. And from either of those, you can convert it to an ONNX model and sometimes convert it back to another framework. It's usually the case that you get good performance in the native framework. But surprisingly, sometimes translating the model into an optimized framework, such as an ONNX model or TensorRT, will actually allow you to get better inference performance from that model. So this is, again, something that you'll consider. And this is why we try to provide a large number of framework-specific model handlers as pre-written model handlers. This means that whatever framework suits you well, hopefully we have a model handler that already accommodates it. However, you can also write a custom model handler if you feel that the pre-written frameworks or pre-written model handlers don't serve your needs. And that's really the last part, is the support in Beam. Because we have that custom model handler option, if you are willing to write a custom model handler, we can literally support any kind of machine learning inference. A caveat here is that what Beam does not support well is model training. So do keep in mind that Beam is a tool for inference across your data set or preparing a data set, preparing the features that you will use to train a model, but it's not very good at training a model, mostly because in Beam you're defining a directed acyclic graph, and training an ML model is essentially a cyclic process. So if you think about what model handlers are already available and easy to use in Beam, this is our current list, although the list is expanding, and we, as Beam contributors, also have the ability to add a new model handler to the repo of whatever we think is missing. I find out of these personally, I use XGBoost frequently for classification. I use PyTorch when a model is not well supported in Hugging Face or by the Hugging Face Transformers package. I occasionally use Onyx when I need to translate a model from another framework that I don't have available. But I would say those are kind of my personal top three. Though if you're a TensorFlow developer, that may be completely different. We try to support everything that we think users need, but if we miss something, we do always accept contributions. So really, some of those are not just model frameworks, they're also model zoos. And while model zoo is the term currently used, this is the image that always comes to my mind when I hear it. But we're not talking about this. We're really talking about a collection of models that you can download, especially pre-trained models that are ready for use. The two main model zoos that we have integrated into Beam are Hugging Face and the TensorFlow Hub. Hugging Face is supported by the Hugging Face model handler and the Hugging Face pipeline model handler for the Hugging Face pipelines construct. The TensorFlow Hub is supported via the regular TensorFlow model handler, and that TensorFlow model handler takes an argument that can be a TensorFlow Hub URI. I think, in my experience, that TensorFlow model handler with the model URI is probably the most straightforward, easiest way to incorporate a model into a Beam pipeline. But the Hugging Face model handlers, while slightly more complicated, do give you a richer variety of models. So it depends on your use case. So let's think of an example of choosing a model handler and implementing it in Beam. The first step is to pick a model. So for the example I'm going to show you, the task is predicting a masked word, where a sentence has one word masked or hidden, and then the model will predict only that word. This can be used for testing, but it could also be used for question answering, where the answer can be defined as one word or one word in an answer. So for this, we've chosen a model. We've chosen this My Awesome EL5 MLM model, mostly for ease of use and because it's small. Now that we've chosen our model, we found it on Hugging Face, and it's supported as a Hugging Face auto model with a pre-trained weights. So that suggests that we should use the Hugging Face model handler to deploy this model in production most easily. Now that we've decided on the model handler, we are going to have to adapt the pre-processing and post-processing functions to prepare the input for this model correctly. Now, there is one caveat, one thing that probably is the biggest trouble for new users of Run Inference, is that in the pipeline, you will be processing the output of Run Inference in your subsequent steps. But Run Inference's output is not merely the output of the model. It is actually a named tuple that we define in that base.py class in our Beam inference repository. And that prediction result includes under its inference member the output of the model. So when you are writing a pipeline and you get a type mismatch that says you're trying to treat something, you expect a string, for example, but you are getting a prediction result, that's almost always because you use the prediction result without accessing the inference member of the prediction result. This is one that has regularly tripped me up, and so I hope that it won't trip you up. So now we're going to go to Colab to look at actually adapting this model to a Beam pipeline. And the example that I'm showing you in Colab is drawn from the Beam repository. It's easy to import any of our Beam notebooks demonstrating the use of different model handlers directly into Colab, where you can run them and update them, change the output. It's one of the best and easiest ways to see examples of the model handlers in use. Okay, now we will go to Colab. So again, this is loaded directly from the Beam repository. And this notebook is showing us how to do run inference with our Hugging Face model handlers. Now, it's a note here that there are 3 different Hugging Face model handlers. The pipeline model handler, the model handler with a keyed tensor, where you have the key and tensor so that you can reference the input often, and the regular model handler tensor, where the key is not part of the inference. In this notebook, first we deal with pipelines, but for today, let's skip that. And we're going to come to using a pre-trained model. Now, for this model, as I said, we're going to be using this awesome EL5 MLM model. And so we get that as our model URI when we're defining our model handler. To instantiate that model correctly, we have to know what the model class is. In this case, it's the auto model for MastLM. The framework is an interesting argument. Hugging Face often provides models for download in more than one framework. So for this case, we are requesting the TensorFlow version of this model. But just as easily, we could put PT under framework and get the PyTorch version of this model. The load model args is saying what arguments should we pass in to the model itself. This allows us to be flexible because individual models often have specific arguments that we cannot account for in a generic Hugging Face model handler. Finally, we say what's the max batch size. Here, because we're using a small model and we're running sequentially on one CPU, we're saying the batch size is 1. So if we look at the actual definition of that model on Hugging Face, we see that it's sparse. But this model does say it's a version, fine-tuned, of the Distil-Roberta base. So if we want to see how to actually use the model, we're off to the Roberta page. So here we can see on Hugging Face how you would run this model in just a regular Python function. This is very normal. When you find a model, you'll see code blocks like this in Hugging Face or another repository that assume you're running within your own self-defined Python function, not within Beam's model handler. So we have to look at this and then map it to the model handler, the Beam pipeline, and the run inference call. So first, we see that the model is getting the model for MastLM from pre-trained, and the string here, Roberta base. We are using the awesome ML5 model or ELI5 model. So we are going to replace that with our model string. We see also this model requires a tokenizer. Tokenizer taken from the auto tokenizer class in Hugging Face. And so we know that when we are doing this, we are going to need that tokenizer. Here we're including the tokenizer inside a function that we will run as a pre-processing function. This will tokenize the input and also mask the last word in the sentence. Remember, this is a model that predicts one masked word in its input. So in the pre-processing, we have to split the text, we have to add the mask, and then we also have to have a tokenizing function, because the model expects a series of tokens that are tokenized with this model-specific auto-tokenizer that we've loaded above. So once we have that tokenizer, an additional pre-processing step is we have to tokenize the input. In addition, once we get output, we have to return it to something that we can read. When we're looking at the original specification, we see that they have the model on the inputs returning logits. So this is the ranked set of predictions with their predicted accuracy. So we can retrieve the token index so we know which word we are predicting. And then we can see which token we're predicting by taking the argmax, the most probable of the predictions. Finally, we have to decode that token ID to get back a word. Now, when we're in our Beam model, that means that our post processor has to do a lot of that work. The post processor is going to get the prediction result. Here, remember that I mentioned what you want is probably in the inference. And indeed, the inference portion of the prediction result is where you will find the logits that you expect as the output of the model. So when you're reading this as though you were going to run it in a normal Python function, remember that this output of the model will always be in Beam inside the prediction result.inference member. Then we do the rest of that post-processing, finding the mask token index, finding the predicted token ID, and decoding the word using the tokenizer. Finally, we'll print the output. So once we have those, the model handler, our pre-processing functions, and post-processing function, the pipeline itself is very straightforward. We're creating some examples to test our pipeline. And here the examples are these 5 sentences. Then we're going to do our pre-processing, add the mask. Here we're adding the mask only to the last word, and tokenizing the sentence. We read as the result a run inference call drawing from those tokenized examples using our keyed model handler. The model handler is what it takes. And we give it a post-processing function. Now, this is one style where the pre-processing function is in a normal Beam pipeline. It's a function executed before the inference, and post-processing follows it. We'll see later in this lecture, another way to do this using the with pre-processing function and with post-processing function calls that we can chain onto the model handler. But here, when we run this code, we see that indeed, all 5 sentences, even with this small model on CPU, we can predict correctly. So this is a good example of the full process of finding a model and adapting it to Beam. And if you wish to use a model with a different model handler, we have similar notebooks for all of the model handlers that are supported in Beam now. So now we'll head back to the slides. Next session, we're going to do a high-level overview of our complex ML pipeline, decoding voice telephone calls, classifying them, getting a response from an LLM, and transcribing that response back to a voice file. Thank you, and see you again soon. Bye-bye.